Hi, I'm Alex McAdams, and I'm a physics programmer working on Chaos Cloth for Unreal Engine. Before coming to Epic, I was an engineer at Disney Animation, also working on hair and cloth simulation. I worked with Jared Monson on Ciri's cloth for the Witcher 4 Unreal 5 tech demo, and we're excited to use this experience to share some of the best practices for using Chaos Cloth in AAA game workflows. It's just a quick video to remind you of what the cloth looked like. So in this talk, we're going to go through the process of setting up cloth assets for a game, from design to rigging and in-game controls, with the inevitable compromises that you end up making when under project deadlines. So before you start building your cloth asset, you'll need to consider both artistic and performance goals for your cloth. Oftentimes, this process starts with concept art like this, sometimes with a few variations. Now can be a good time to raise potential simulation issues and brainstorm solutions. For example, this version of Ciri's cloak has a lot of small folds that can pose simulation challenges, both in terms of resolution required to simulate the folds, as well as the number of potential self-collision issues. Thankfully, a heavier, simpler to simulate version was ultimately chosen. Now, when determining the level of detail we want to include in our simulation proxy mesh, we need to consider both performance targets and art directions. In particular, for Ciri, we had a budget of under 1 millisecond on PS5, and we knew that her cloak was made from long, heavy material. Furthermore, we had to prepare for complex collisions between Ciri's body, swords, and the horse. While Chaos Cloth has a wide range of features to support anything from real-time game simulations up to cinematic quality cloth, we'll be focusing on which settings are appropriate for game quality cloth in this talk. In particular, when targeting a typical game, we recommend simulation meshes with a resolution of around 200 to 600 simulated vertices. Significantly more vertices can push into the cinematic cloth quality, which can require more complex setups. For setups with a typical level of features for cloaks and capes and things like that, we tend to recommend around 350 simulated vertices. This allows for enough degrees of freedom while staying in a half to 1 millisecond range on current generation hardware. I also wanted to highlight that for 5.6, we've done some optimization targeting platforms such as mobile, and have found that around 200 simulated vertices works well, coming in at around 1 millisecond per frame on these platforms. So once we've got the specifications for our cloth asset, it's time to rig it. One of the first inputs you'll need to generate for your cloth asset is your simulation proxy mesh. We've talked a bit about the recommended resolution, but we also need to consider things like edge flow. The main thing to remember when creating your simulation mesh is that cloth can only bend along mesh edges. At cinematic quality, this can have an effect on wrinkle bias, but mostly you have enough degrees of freedom to bend any way you want. On the other hand, on this game quality, edge flow will have a real effect on the bulk behavior of your simulation. The right image here, it shows the simulation proxy we used for Ciri's cloak, and we found that similar quad-based meshes with attention to diagonal triangulation tends to work well when making similar cloaks and capes. We have a few different ways to import your meshes into the cloth asset, but one that gives the most control is by importing from a skeletal mesh. The cloth asset will import both the mesh geometry as well as any normals, UVs, skin weights, and render colors and materials. And new in 5.6, we also support importing simulation morph targets. Another type of asset you author outside of the cloth editor and import in is the physics asset. This asset contains kinematic collision bodies for the simulation that are driven by a skeletal mesh. While the physics asset supports a range of types of collisions, including convexes and skin meshes, We recommend using simple rounded primitives like this, so tapered capsules, capsules, and spheres wherever possible. They're both performant, and they lack corners that can cause snags. Once you have these assets, we'll use the Chaos Cloth editor to do the rest of our cloth asset rigging. The core of the Chaos Cloth editor is a data flow graph. This node graph is a construction graph made up of nodes corresponding to operations like adding constraints, remeshing, painting weight maps, or editing solver settings. The terminal node of the graph compiles this data into the final cloth asset. The editor has two viewports, which you can see here. The construction viewport, by default, is on the left, and it corresponds with the state of the asset up to the currently selected node. From here, we can view the asset's three sets of geometry: the render geometry, the 3D simulation proxy, and a 2D panel-based version of the simulation proxy. The right-hand viewport is what we call the simulation viewport and can be used to preview your cloth asset with optional animations, and also that's where our simulation debug display is. If you're familiar with the skeletal mesh-based cloth editor, this corresponds with the viewport there. If you're interested in learning more about how to use data flow, I'd recommend you check out the non-destructive workflows for chaos physics in UE5 session later this afternoon. Now, Chaos Cloth offers several types of constraints, but some of the biggest decision points are which constraint types to use for stretching, bending, and self-collisions. So I'm going to walk through these options and our recommendations for game assets. On both our stretch and bend simulation nodes, one of the properties you'll find is solver type, with the option of PBD or XPBD. For assets with the resolution we're using here, we recommend using PBD. It's computationally fast and has a simple to author 0 to 1 stiffness values. The main feature that XPBD offers is constraint damping, but we found this feature is more useful for the high resolution cinematic quality cloth with high subframe counts. Now let's take a look a little bit more at our stretch constraints. The first checked box you'll see is whether or not to use 3D rest links. You want to keep this checked on unless you have a simulation mesh that was authored in a panel-based cloth editing package that can be used to generate a size 2D mesh. So the top is an example of where we do have that 2D panel mesh that's the correct size. But in our case, we have just a simulation mesh that was generated from the 3D render mesh, so we'll be using the 3D rest links. Once you've done those first two selections, you can also have the option to add an area constraint, which can add extra stability to the simulation. I recommend adding it depending on which bending model you choose, so I'll talk about this a little bit more in a bit. The last stretch constraint option I wanted to highlight was enable stretch, warp, and weft scale. This allows you to change the rest length of the mesh. Oh, sorry, I realized the video wasn't playing. This allows you to change the rest length of the mesh at runtime. So that was stretch constraints. Now let's take a look at bending constraints. The big choice you have is between what we call hinge or faces spring. The hinge constraint is an angle constraint on each edge of the mesh. The faces spring is a spring that connects opposite vertices from an edge. So the hinge is like the constraint on the blue, and the faces spring is the red spring. Hinge constraints are good at holding a specific angle and work well for cloth that has a lot of structure. We use them on Ciri's hood for this reason. One drawback of the hinge constraint is it can be less stable under a lot of stretching. And this is part of why we like to use it with the area constraint I mentioned before. The faces spring constraint is good for softer, more dynamic objects like the cloak. This constraint is very cheap and stable, but it can't hold specific angles as well. So the final simulation property choice I wanted to talk about is our self-collision options. The most expensive option is the full self-collisions with self-intersection detection. This is all the bells and whistles with per vertex thickness, full layering, and intersection resolution. But it can be very expensive, and it would have completely blown up our sub-millisecond budget. For this reason, we have a much cheaper self-collision sphere repulsions. The simple repulsion spheres, they're cheap to calculate, but they don't know how to untangle the cloth if they all pass through each other. This is where our new cloth-cloth constraints can come in handy. Cloth-cloth constraints allow you to generate springs between arbitrary cloth points. Currently in 5.6, we have a few different procedural methods to calibrate these constraints within the cloth editor. The main feature that makes these useful for supporting self-collisions is that you have a separate compression versus extension stiffness. So in the case of Ciri's cloak, we set the springs to only engage when they shorten beyond an initial configuration. This keeps the cloak from collapsing in on itself while remaining free to expand out. The last configuration node I wanted to talk about is our solver settings. Solver settings control how each frame is subdivided. The first level of this subdivision is the number of substeps per frame. In this case, we have 2 substeps per frame, denoted in orange, where the total cost of the frame is equal to the substep cost plus a fixed frame setup and finalized cost. Each substep is further divided by a number of iterations. Here we have 2 red iterations per substep. Similar to the frame level, there's also an additional cost per substep, where we advance time for kinematic objects, as well as set up self-collisions. We recommend starting out with a minimum of 1 substep, one iteration and 1 substep, and testing with it, only increasing substeps and iterations to improve fidelity. In particular, if you find you're missing collisions, increasing substeps can help. Substeps are also helpful when improving constraint convergence, for example, reducing stretchiness. Increasing substeps will also reduce the amount of numerical damping in your simulation, which can make the cloth overactive at higher substep counts. This is why we have that XPBD constraint that I mentioned earlier. One way to increase convergence without this effect is to instead increase the number of iterations. Increasing iterations tend to be less effective at improving overall convergence than the equivalent number of substeps, so it may take some experimentation to find the right balance. However, in this case of Ciri's cloak, we use 2 substeps and 2 iterations, which tends to be common for simulation meshes of the size and weight, especially when you have the more complex collisions that we had. So that's it for the basic cloth asset rigging guidelines. Now I'd like to hand it over to Jared to explain how to take these building blocks and build a game-ready cloth setup.
All right, thank you, Alex. My name is Jared Monson. I'm a senior technical animator at Epic and was working with Alex, obviously, here on the cloth. It's awesome when you have good engineers because it makes my job a lot easier. And when I say, hey, I need this thing, the physics engineers are great and are able to give me the things that I need most of the time. So, all right, so for my portion of the talk, I'm going to kind of focus a little bit more on conceptual things and not so much on like individual nodes and settings, simply because I feel like everybody's projects is going to be different, and what settings or values might work for me may or may not work for you. But we do have similar problems, and so I want to, like I said, focus a little bit more on approach and some of the things that I use to help solve some of those problems. There's a lot of great docs and even other talks as well, both here at this conference and online, as far as helping you get a little bit more into some of those individual nodes and settings. So I definitely recommend checking those out. So let's move on. So we learned a lot, obviously, in this demo and how cloth can work in a more game type scenario and production environment. So what I wanted to do is kind of break my area into these focus areas, and I feel like each of these areas is pretty important to help you solve problems that you might have. So something that I'm calling the cloth controller function. We'll talk about the velocity scale node, your animesh poses, attribute maps, and then also the editor CVARs to help you debug and see what's going on in your cloth setups. Before we get too much further, though, I did want to talk about the kind of important and how it's important to understand the difference between the cloth component and the cloth interactor. The cloth component is the component itself, and those it sets component level attributes that affect the whole cloth, like adding and remove collisions, teleports, resets. It handles whether it collides with environmental objects and things like that. So it's more of the global values. And then the interactor is what you need to set dynamic values in the cloth asset itself. So these are the things where I want to change, velocity, scale, or friction, or dampening, or any of those things. And that's the variable or interactor is what you need to help set those on the fly. And to get the interactor, you start with the component. It's derived from the component itself, and then you can set, like up here, there I have an example of setting friction. So the cloth interactor is really important to have. That's the thing that we set it. So let's start off talking about the cloth controller function. This is, like I said, it's the heart of the cloth setup, and it's basically a state machine for Ciri as she walks around. So this function, I realized that one set of values just wasn't going to work for all the different things that Ciri was doing, whether walking, running, on the horse. There were certain scenarios, like when she was on the Vista, and we needed some more dynamic wind, that just one set of values is just not going to work. So what this function does is basically go through, and depending on what she's doing, it sets certain states, and then based off those states, I set cloth values. For this demo, I essentially split this into two functions: one that set the current state, and then one that set the values based off the current state. And for this demo, she didn't do any combat or anything, so it was relatively small. But I recommend if in a bigger game, you probably want to plan ahead a little bit and organize this, because it could get kind of pretty big pretty quick. So to keep me organized, I created a struct asset with values that I wanted to change for each state. And you can see just over here where I have a default state, which was when she was walking, and that was what I set everything off to look good by default. And then for running, mounting, canter when she was on the horse or galloping, and then also I have a special settings for when she was on the Vista. So I set up the struct asset, and I would, this was kind of the first time that I had set this up, and I would err on adding more attributes to the struct than less attributes, because it's always easier just to, it's easier to have those than go back and add them. So if I was to do this again, I would have probably added more cloth values by default. And then for perf reasons, you're probably at some point would want to nativize this as well, this blueprint. Okay, so the cloth controller function reads in various variables like booleans, like is she on the horse, and floats like speed2d, how fast is she going? And then based off of those values, cloth attributes are then updated on the fly. At the Vista, a state set where says, hey, I'm at the Vista. And then I change and update wind variables and wind values, things like lift and drag and a bunch of other things, just to get a little more dramatic effect for when she's at that spot. And then when Ciri mounts the horse, I have, on the animation, I set a meta curve that just says, hey, this is the mount left, or this is the mount right. And then based off of those, I set, actually use a little bit of wind values and other things to kind of help get the cloak up and over there, and then set friction and a bunch of stuff like that, just, again, based off of whatever she's doing. All right, let's talk about velocity scale. Velocity scale is a node that's in the cloth graph, and it is huge to help control your simulation. So the velocity scale controls how much movement is inherited from the world space, and there are clamps for velocity and acceleration, as well as like an overall scale. And this video just shows a quick example of how that affects, how it can affect your simulation. And I set velocity scale on pretty much every state she's in. It allows you to control all the motion that's coming into that simulation. So that's the node, the velocity scale. You have both linear and angular control. And then so there's a velocity scale, and then there's also clamps. And I prefer to use the clamps on the velocity over the scale, because in the scale node, or excuse me, Alex and I were talking earlier, is a good example. Scale, if somebody's running at 1 mile per hour at a fastest scale, essentially just, if you put it at 0.5, they're now going, it acts like he's going half that speed. Versus a scale clamp, or excuse me, versus the clamp, it doesn't do anything until it hits that point and then clamps it, won't let it go any further. So I felt like the clamp worked really well, because I still wanted a lot of motion and activity, I guess, in the cloth. And the scale worked really well, and the clamp worked very well because it wouldn't let too much information get passed into it. Here I set the max linear velocity based off of if Ciri's running or walking, and then the velocity scale is a vector value, so you have control over X, Y, and Z. To avoid popping between the transitions, I also created an f-interp function that just smooth blend between the different values, so you didn't get the pop. Wrong button. There we go. This video shows the effective velocity scale as Ciri is walking and running around. So more motion is applied in the forward axis to help push the cloak back, and also in the up and down axis to give a little bit more movement up and down. So one of the problems that we ran into was the collisions on her feet would sometimes get caught up in the bottom of her cape because it's pretty long. And so just giving a little bit more velocity in that direction just helped push it out a little further. The same principle is applied to Ciri when she's mounted on the horse. So based off of speed, I update the velocity scale, as well as lift and drag and friction, and also the warp weft scale. I also I end up shrinking the cape a little bit, just to, we didn't want to cover up all of the horse with her cloak, and it also just made it behave a little nicer. So yeah, she goes into gallop, I ramp into some different variables just to help get that cloak up and make it look a little more dynamic. All right, let's talk about the anim mesh. So in your cloth asset, you have the simulation mesh, and then you have the render mesh. And the simulation mesh is based off of your anim mesh, or it's the base mesh. And so consider this is essentially the foundation of your simulation. And that anim mesh totally influences influence what your simulation is doing. So like max distance, anim drive, backstops, resets, they're all based off of your anim mesh position. So in here you can see the base pose for when Ciri is riding on the horse. That purple mesh it's swept over to the side to keep it away from the scabbards, because the scabbards were very tricky, and it would get caught up a lot. So we helped art direct it to that side, and then just to help keep them away and also avoid penetrations with the other saddle and other things in the back. This is Ciri's base walk pose, or just when she's running around. So the other thing was we wanted to make sure that that purple mesh wasn't clipping with the scabbards by default, and I kind of spread it out a little bit just to help. I felt like it gave it a little more flair when it was walking around. And all of these same things apply to the hood as well. I have a base mesh starting pose for the hood, and again, same principles apply for that. So you can influence the sim mesh by rigging and posing the animesh, basically giving you art directability. So you can see here the pretty basic rigs set up in the animesh, and you could go as crazy as you wanted, but you don't have to have it. But again, that gives you the ability to art direct and kind of guide the simulation a bit more. One of the cool things that Alex mentioned as well is we just added morph targets, which is really super awesome, because one of the things we ran into is the hood we would animate down, and while it worked pretty well, it still was a little bit crunchy as far as the mesh goes. The meshes weren't super clean, and so I was like, hey, Alex, would be really cool. And so Alex hooked me up, and so now we have morph targets so I trigger a morph target in the animated pose just to clean up the edges, and then it really helps the cloth behave a lot nicer. And we could have done that for the horse as well. Like you could even have a nice simulated pose on the back of the horse and then use that. All right, so attribute maps. This is something that ended up being a kind of a bigger deal than I thought it was going to be. So obviously you have attribute maps that you paint in the cloth asset editor for max distance and all your different things, which is really cool. But something that we ended up doing was it's possible to swap maps on the fly. So going back to the hood, when the hood was up, I had a max distance map painted and that worked really well for when the hood is up. But at any point in time, Ciri could take her hood on or off. And when she took it off, like the map worked, but I could see a little bit of kind of fighting and stuff like that. And so I ended up painting another map for when the hood was down. And then I have a variable again that says when the hood's down, we swap maps and then use the map, that max distance map, which the hood is down. And that, again, just gives me another level of control that when it's down or in a different position, we can swap it on the fly. And then I just hide the transition, or I had the pop essentially when the hood is going down. So again, depending on whatever situation and you could swap maps, which is really cool. All right, so let's talk about some CVARs. CVARs essentially are debug features that help us see what's going on in the engine, and they're really important to help debug and understand what is actually going on. So here are some of the CVARs that I use the most, and I just wanted to highlight them because, again, I think they're super important. So the first one is, well, let's start over there. So in order to turn or see any of these, you have to have the debug enable function, so that p.chaos debug enabled. That one turns the debug draw on or off. You have to have it on to see any of these. So once you have that turned on, the one kind of in the top left there is the debug draw collision that actually shows you your collision shapes and for just the cloth asset itself. And so you can see what's going on there. The next one is the animesh, which is the purple one. Again, that showing what's my base mesh doing. That was a huge deal for me to understand what's actually happening. Is it in the right pose? And things like that. Another one is the debug draw teleport reset. This is a new one that Alex added, especially during cinematics when we would get pops in between transitions. We weren't sure, was it teleporting? Did it reset? Like what happened? And so that will turn green, that mesh will turn green if there's a teleport that's happening, or it will turn red if a reset is happening. So it helped us understand, what just happened. And then the other one in the bottom right here is, you can hopefully kind of see it in the transition, but it's the drawn foreground. So by default, the wire mesh draws through the mesh, and I find it to be kind of distracting and not super helpful. So that actually makes the wireframe not draw through, and is something that I like to use most of the time. The one other CVAR that I ended up using a lot is the T override FPS, and what that does is it forces Pi to use whatever frame rate you specify, even if it has to slow down the play rate. And what that does is essentially gave me more accurate visuals in the editor for what the cloth would actually do when it's running at actual 60 FPS. So sometimes in Pi, depending on various performance things, you may or may not get super accurate results, and so this helped really dial in. And then actually one trick that I use this a lot too is going through cinematics. Sometimes we had long cinematics. I would just turn the frame rate to 5 FPS, and then it would just essentially fast forward so I could just see the part that I needed. So a little trick. So there's a ton of CVARs, and depending on what you're doing, it's really hard to remember all of the things and what they do. So income editor utility widgets. So utility widgets are really great for this very thing. This is just a small example of what I did. Based off all the different things, I just made a little widget with easy buttons that just turn on and off CVARs, which really helps speed up time and debugging, because trying to remember the exact names and everything like that was pretty difficult. So the nice thing about utility widgets too is they're actually really easy to just move on to other projects and things like that, copy over, it's, in my opinion, totally worth the effort making a utility widget, especially for a bigger project where you're going to be doing a lot of work. All right, let's talk about just we call the special case toolbox. There's every project that has, you kind of have like your main flow of things, and you kind of figure that out, but then there's always exceptions to the rule. And so these were some of the solutions that I did to kind of help for those more unique solutions. All right, so we'll talk about the Vista Wind, show you some collision tricks, how I use control rig, and then some things that we learned from the cinematics. So the Vista Wind, there's a volume trigger set up because it was a very specific, unique area in the world, and we knew at that specific point we wanted to have specific things done. So I just set up a volume trigger, which has an overlap event that says, hey, I'm at the Vista, and then based in the controller function, I look for that variable, and when it's at that variable, I set those specific wind values and like the cloth attributes like lift and drag and all that kind of stuff. Again, just to get a more cinematic, a little more dramatic effect there. And that's the only spot I use those values. So one of the great things is to be able to dynamically add and remove collisions. So by default, Ciri doesn't know, the cloth doesn't know about the horse and has any collisions for that in the physics asset, because you don't want to carry around all those extra physics assets or physics capsules when you didn't need to. So the add collision source is a node that you can use to dynamically add and remove collisions. So when Ciri gets on the horse, we run this function. I set up those collisions on the horse asset itself. We trigger this, it adds those collisions. So then now when Ciri's on the horse, the cloak can react appropriately to what's to collide with the horse. And then when she gets off the horse, we dump those collisions so we don't have to pay for them or use them anymore. And the cool thing for this as well is that works for R-band as well. So any like rigid body dynamics, you can dynamically add and remove. So if you had like a backpack or something in a hair and you needed to collide with that, you can add and remove collisions. So that's a really cool node. One new feature we added to capsules was a one-sided collision. It might be kind of hard to see, but in the top, one of the issues we had with a collapsible and kind of the tail of the hood was as Ciri's head would turn, it would kind of wrap around the capsule. And so what this one-sided collision does is in the positive X, it always pushes out that way and just helps prevent your cloth from wrapping around basically to the backside. The other thing is, so we mentioned this before, the scabbards were always really tricky to keep them out of the cloth and getting tangled up. And so during the mounting sequence, I actually do have a bone above the collision object that I just animate up a little bit out of the way. So as she's kind of throwing her legs around, we just slightly move those scabbards collisions up out of the way, just give it a little more breathing room and get over to the edge. So when it can get over the horse, and then we can slide them back down once it's there. So just feel free to cheat. External collisions. So in the demo, there's this little sequence right here where she goes through the kind of a tight spot in the cliff. And collisions can be, or external collisions having on all the time is kind of expensive. And so it's the same trick here. I had a collision box that said, hey, I'm at the spot. I temporarily turn on the external collisions. And then in the collision, in the world, we have a couple capsules set up against the cliff there. And then as she goes through it, we get a nice collision with it. And then as soon as she leaves it, I turn the collision back off, so we're not paying for it. All right, control rig. One of the other issues that we kind of ran into, so the hood by default in the skeleton is parented to the base neck. And so, which is great for when the hood is up, it follows the head and does what it needs to there. But when the hood is off, I didn't want it to follow the neck, I wanted it to follow the spine. And one of the problems too with that was the animesh, when it was rotating with the spine, it would like kind of clip through and push through some of the shoulder, causing it to really get jittery and cause some problems. So we came up with a pretty easy control rig to simply basically follow the neck when the hood is up and follow the spine when we were done, or when it was down. So really easy and worked really well, and saved us a bunch of heartache actually. So also control rig, there's this, it's called the spherical pose reader, and this is one of my new favorite functions, but basically here we have, again, the hood tail with her scabbards. It was clipping and just like, it was just right at the perfect spot to cause problems, basically is what it was. And so with this spherical pose reader in the animesh itself, what I did was set up that vector, and you set up that the sphere and the green spots where it's 100%, and then it fades off basically based on that. So as she turns her head, I just physically animated that tail down to get it out of the way and to help the cloth and collision just not have to fight so much against the capsule for the scabbard. I also do that for the arm swing. So as Ciri's kind of walking or running, we were getting a lot of kind of like just issues from hitting her elbow against the cape. And so same thing, I have a vector that points down to a pose reader. And then as her arm basically gets to this position, I essentially push back. There's a joint on the cape that I just push back a little bit and kind of rotate. And again, just gives it a little more breathing room and doesn't have to fight so hard with the collision. All right, let's talk about cinematic sequences real quick. So pre-posing. Pre-pose if possible. So put characters in the correct pose on the frame before the cut, and this will give physics a chance to to get into the right pose and settle before you actually get on the, actually view that camera. It sounds simple, or it sounds straightforward, but it makes a huge difference. It really does. That's not always possible, but especially when you do, like you're doing back and forth cutscenes between characters, if you can keep the characters within relative position, it makes a huge difference. We fought a lot of pops and different things like that, and just pre-posing made a big difference. Event tracks. So in sequencer, although sequencer evaluates ranges of time, property tracks only apply the keyed value of the current time, regardless of how many keys we've crossed between the last frame and the current frame. Basically, keys, depending on your current time, it's possible for them to get skipped. So event tracks are different. They will deterministically trigger in the order they appear on the timeline and are guaranteed to be triggered even if they don't land exactly on an evaluated time. So if we have, say we need to do a teleport or a reset or something on the clock, on the cloth, and you set a keyframe, depending on how good your frame time is, it may or may not get evaluated, versus an event, it always fires. So things that are really critical and that you need to hit for sure on certain frames, use events. Okay, so shot specific functions, creating specific functions in the blueprint, the sequencer blueprint. It gives you that opportunity to, for whatever that shot needs, you can kind of do a little bit of magic there that only applies to there. We'll talk a little bit real quick about teleport and reset and how we tackled some of those. This is kind of my order of operation. First, do no harm and teleport. Teleport removes any external forces and essentially pauses the current pose of the cloth and then resumes it in that same pose after the teleport. And this should work for most situations, especially if you pre-pose or anything like that. Teleporting is usually the best way to go. The next one is reset. Reset will restart your simulation based off the current animation pose. So going back to that purple wireframe, whatever that pose is in is what reset will put your cloth in. So if for example, if Ciri was on the horse and her cloth was in the walking default pose, that's just down, and I hit a reset, that would start the cloth inside the collision, and then it would pop out. So it's really important to make sure that your animesh is in the right pose, especially when you do reset. Sometimes that doesn't always work, but global dampening is the next one that I use a lot, where I had a function that would turn global dampening all the way up to 1 just for one frame, and then I'd ramp it back down, and that seemed to work very well. All right, so one of the things that, I wish I'd known this before at the start of the project was the fur cards ended up, I wish what I had done is on the simulation mesh. Right now the simulation mesh it just does the main cape. It's in the shape of the main cape and doesn't take into account for the extra width of the fur cards. I wish I had gone back and made the simulation mesh go all the way out to the edges of the fur cards. It would have mapped a lot better in the proxy node, and then the collisions would have been better because you have an actual edge on the fur cards, and that would have prevented some kind of weird pops that happened there. So that was one thing that I wish I had done more. All right, so again, knowing that we had a 60 hertz frame target and 300 plus simulated vertices, we knew that there was just going to be some compromises, because man, we had to hit those targets, and we knew we couldn't have it all. So some of those things were like juicy folds, right? Because there's only so much resolution, and like every vert counts. Like getting super intricate folds just probably wasn't really going to be that big of a reality for us. Perfect collisions, again, we're working with low res. While we had really good collisions, actually, I think we did really well, and we were able to keep the cloth out of the scabbards, which was a big deal. We still were able to make it work. You're going to have a low vert count, especially if you're going to be hitting performance targets. That's just a reality of it right now. And then corrective blueprint work will be likely, like I showed you in the cloth controller function. There's just, again, you can't rely 100% on the simulation itself, like self collisions and things like that. So you're going to have to do a little bit of fix-up work to help smooth things over. So hopefully we've shown you that you can get really great results with Chaos Cloth in games. I'm really happy with how things turned out, and we thought it worked and looks really good. And hopefully, this inspires you to do more cloth in your games and projects. And with a little bit of hard work, you can have really awesome cloth as well. Thank you, appreciate it. We'll do a little bit of Q&A. I'll have Alex come back up. I appreciate it, everybody coming today, and hopefully this will help.
sense. Cool, man.
Okay. Welcome, everybody. It's good to see you all here. I hope you've been having a great UEFest this week. Today, we're going to be looking at seamless transitions to cinematics and timeline scaling. Hopefully, that's the right talk that you were expecting. Otherwise, you might be in the wrong room. You need to find somewhere else. So this is what we're looking at today. Hopefully, we have some time for Q&A at the end as well. Okay, so who are we? I'm Andrew Rodham. I work at Epic Games on the animation team, mostly in cinematics and sequencer.
And my name is Rafał Kruk. I'm a senior cinematic designer and coordinator in CD Projekt Red. I'm also a StoryTech power user, helping to shape up the tools for cinematic design and narration in general. Work in CD PR for over 6 years. So just a quick note that the techniques shown in the Witcher 4 Unreal Engine 5 tech demo are still under active development. So the content we will show here is not necessarily representative for the final Witcher 4 game, obviously. Also, some of the editor examples will be shown straight in sequencer, so not in final quality. All right, so without further ado, let's kick things off with looking at the very hot topic, seamless transitions. So here's a quick edit of some of the transitions, moments from the demo, which we will unpack in a moment.
Let weeds be weeds, Kelpie. A typical day's toil.
Who in? Ah, Witcheress.
Right. So yeah, at CDPR, we've always designed our experiences to be as immersive and engaging as possible, and we deeply focus on that. Bringing cinematics closer to the player, meaning that the game experience is uninterrupted, and you never feel detached from your protagonist. You are the character on screen, so instead of feeling that the story is being told to you, it's about you seamlessly soaking into the narrative and making it your own unique experience that you can relate to. So any narrative designer in the room, not only a narrative designer, will know that we often employ a lot of tricks to get that perfect transition. It always begins with the design. The approach to any narrative beat is discussed with level design and enviro in order to coordinate that perfect cinematic handoff. Locations should be secured to lead the player to a specific spot, and the path leading to the destination should feel intuitive and convenient. And in this case, another gameplay scene was added to catch your eye from distance, anticipate, and give you enough context for the transition. It has to feel natural. There's action in front of you that makes you want to participate, so when you lose control, you are well prepared. So let's rewind that and look at it from a slightly different perspective, because we can use a full spectrum of narrative means to prepare the player for the transition from full interactivity, which is gameplay, to full linearity, which is cinematic. Those means could be, for example, using camera cues, like now changing the FOV. We can also use limiting gameplay systems, such as slowing down the locomotion, forcing a weapon down state, disabling magic, clearing HUD, you name it. And before you know it, you are already in a cinematic. So there's a Polish saying that says, if you don't have what you like, you better like what you have. And this pretty much sums up the situation in which you're not having, for example, enough budget to implement more advanced solutions, or solutions like you've seen before, or you need to implement solutions to hide technical issues. So the simplest example would be the good old cut from gameplay into cutscene. I implemented this really quickly in sequencer, so you can, just to sell in the solution.
Get your ass up.
A typical day's toil.
Who win?
So this solution pretty much solves most of the problems for you, and which is not necessarily bad if you want this solution, but on the other hand, what if you don't? And the thing is, it's not about, it's not about if you want it or not, it's mostly about consciously acknowledging the fact that it will change the cinematic experience. So wouldn't it be great to, freely decide upon your game design and not only be sentenced to your own limitations? And I know what you're thinking, it would. But it never happens in game dev, right? So here we are stepping into the topic of the stitch track. It's a big step towards giving us, designer, the freedom of choice where gameplay meets cinematics. So, Andrew.
Yeah, so thanks, Raf. Let's take a look at how we actually apply those design principles and implement them using some of the examples from the demo that we saw earlier this week. So how do we get from the camera cut, which Raf was showing here, which we all know and love, to this beautiful, seamless transition that keeps the player immersed in the experience without causing immersion-breaking bugs like this? First off, it's important to stress the importance of designing your gameplay input, animation, locomotion, and camera systems to support cinematics as a first-class citizen early on in development. These systems and techniques involved are multidisciplinary, and they require careful planning and cross-department collaboration to ensure not just the best final quality experience, but also the smoothest production schedule. Neglecting to integrate cinematic control into your gameplay systems early on will result in hard-to-fix bugs, costly iteration, and fragile cinematic design that's prone to regression. So in order to get the best results, we need to employ a systematic approach and coordinate cross-team efforts to create a cohesive and immersive player experience. Broadly speaking, we can approach the strategy in 3 overlapping phases. Firstly, how we might work with environment design, camera direction, and player input constraints to guide the player towards the cinematic moment. Secondly, how we incorporate cinematic transition into our gameplay input, camera, and animation systems so that we can blend seamlessly and maintain immersion. And finally, how we relinquish control back to the player and to other gameplay systems when the cinematic is finished in a natural, fluid, and predictable way. So first, let's look at how we get the player into the cinematic moment. As Raf mentioned earlier, we can use a variety of techniques here to draw the player into the cinematic. And we've got a few tools at our disposal here, which can be tailored to fit the feel of your game. Here's an example from the demo, how we used heavy environment design to create a gully which leads the player towards the trigger that initiates a stitch animation into the cinematic. But you might also choose to constrain your player input where environment and prop placement is not an option. So once we've hit the trigger and we actually initiate the cinematic, let's look at exactly how we stitch the animation together in a way that works to create a continuously fluid motion towards the starting pose of the cinematic. This is where the experimental Unreal Animation Framework has unlocked a substantially greater level of power and control over animation in Sequencer. As part of Sequencer's integration with the UEF, we've introduced a new track called the Animation Mixer, which deeply integrates into UEF and provides some additional functionalities over what the animation track currently does. These features are all experimental in 5.6, so they can be a bit rough if you want to try them out, but they can be enabled with these plugins here. The Sequencer Anim Mixer enables the actual track, and the Movie Scene Post-Search Tracks plugin it enables the stitch track implementation, which integrates into motion matching and our post-search technology in Unreal. So fair warning, they are early in development, as is UAF. So they may be subject to change in future, and I said on my notes here, they may have some stability issues, but they definitely will have, and some usability issues. So we're excited to bring them and to announce them here today, and we'll be working on more updates in future releases, and we'd love for you to try them out and give us feedback and suggestions early so that we can work with you guys to improve them. Okay, so how do we actually perform an animation stitch? Let's look at that in a bit more detail. So stitches leverage Unreal's motion matching technology to match animations from a pose database using an input pose and a trajectory, a target pose and transform, and a duration. This powerful feature is a great tool for procedurally filling in gaps between gameplay and cinematics, where we're required to match an unknown state and position from gameplay and match it to a predefined starting pose for the cinematic, such as when the player triggers from a trigger volume. For those that are unfamiliar with motion matching, in high-level terms, the pose database contains a dense set of animation data within which the algorithm can select portions that match a given criteria. And the pose search schema defines a set of rules which specify how to determine the quality of a match within that data. So to give a simple example, we might want to match a character's current feet position with the predefined foot position from the cinematic that needs to happen 2 seconds in the future. With the feet position assigned as rules in the schema, motion matching can quickly select an animation that will get your player to the desired foot position as closely as possible. If the selected piece of animation for motion matching is slightly different than the duration that we needed, or doesn't get us slightly to the target pose exactly, then the stitch section will warp the animation to fit so that it matches the target exactly, to account for gaps in motion matching coverage. Here's an example of what a stitch database might look like if we want to stitch gameplay animation from various different approach angles and walk phases in a way that converges on a single point. Although on the screen you see the animations diverging, they're taking different paths from their starting position. And it's important to remember that motion matching will select any of these animations and rotate and warp them to fit the target pose based on your schema. This is where it's good to experiment with different databases and schemas to get the best results. If you have a wider set of entry conditions, such as wider approach angles and speeds, you may need more animations to ensure that you have enough coverage in the database to yield the best results under those circumstances. The key here is to experiment with different schema settings and pose database animations to help tune the stitch for the best coverage. You can place hand-keyed animation in here that you may have retrieved from your animation team, or you can use recorded animation from gameplay. And this is actually how we recorded everything for the stitch databases in the Witcher 4 technical demo. So here's a quick tip. You can actually record gameplay, and you can use Take Recorder to do this, or you can use Rewind Debugger. For those not familiar with Rewind Debugger, it's a great animation debugging tool in the engine. Definitely check it out. It's a great way to quickly generate the coverage you need when you don't have enough source animation data, but you do have motion matching already set up in your project. If you use Rewind Debugger, we recommend using t.override FPS and fixing the engine to a fixed frame rate, which gives you really smooth animation data once you've baked it out. And then you can use the trajectories drop down here and choose Bake Out. And here's what it looks like just using echo from the animation sample. So here I start recording, and I'm going to run echo around a few times using different curve angles, which is going to give me some good coverage in the database. And I stop recording. This is all fixed at 60 FPS. I choose Bake Out, and it opens this window, which allows me to choose the character mesh. And as you can see, that's the recorded animation. I set the export frame rate to 60. Give the anim sequence a name. I also force the origin, which sets the origin to the first frame. And you can also trim the animation as well to choose which portions of the recording you want to export. And you hit Bake Out, and you get an anim sequence on the other side that you can drag into your pose database. So here's what the result looks like in a gray box gym. When the stitch begins evaluating, it will take the current transform of the animated object, and it uses that to generate a trajectory towards the target transform, specified on the section. These are all on section properties on the actual stitch section in Sequencer. You can right-click and you can find the target transform and all the pose database that you want to use there. And it will select the best animation from the database and warp it towards the target pose. And in the context of the demo is another look at that. So this is the example with the gully. Here's what it looks like in Sequencer. So we have our stitch section here on the new Animixer track. We're going to blend from gameplay. We're actually leaving the player in control of the character during that blend. We then disable locomotion, let the stitch play out, and then we blend into our cinematic. And I'll just let that play through again so we can get another look at it. So we blend from gameplay while the player is still in control, and we're actually gradually, over time, overriding the locomotion animation from the player character there. There's no transform tracks here. It's all done in the Animixer. And then we blend into the cinematic. And over to you, Raf. Let's talk about the new tools.
All right. So yeah, let's talk about animation with motion and the features that were, made stitch track kind of easier. So let me give you an overview of the properties in Sequencer first, and I'll lead you through an example right after. So the new root motion section in Sequencer enables precise control over how root motion is handled for each clip. It allows to both control the root bone transform per clip and keyframe how root motion is applied to the target as a whole. For those familiar with the existing animation track, root motion track is equivalent to the option, if you right-click on it, to the swap root bone setting. Only it has more options, keyframeable, and exists as a single track. The drop-down you can see here discards the root motion, applies it to the root bone component or actor, or leaves it on a custom attribute that can be picked up by mover. Also, 3 modes exists for the root motion transform: asset, offset, and override. And these controls remove the need to keyframe objects, transform track at all, which eliminates the glitches that we know. So let's have an example now. We will combine 2 animations. We have like 2 animations with moving root. One animation here and the other one, and you can see that the root is moving. And we will lay them out in Sequencer, one after another, and try to blend them together. And with the animation mixer, it's as easy as just dragging one animation above the other and just setting the blends. And as you can see, there are no transforms involved in that. And when you play, you can easily see that those animations are blending. It's just that the position is not correct. So what we can do here is, we can control it with X, Y, and Z. So we can eyeball it and do the math. But here, under 1 minute, we tweak it a little bit more. We can see that the blend is almost perfect. So let's add a camera cut to this one. You can see that it blends. We can add a camera cut and make, because if we would like another shot, see that if we play it, she comes closer to the camera. But for some reason, we would want her to come closer, not move the camera closer, we move her closer. So what we can do here is select the first step so we can animate the root motion in Sequencer, select the position where she stops, move her closer, and with just 2 keyframes, you can see that the root motion is animated without any glitches, because the transform track is not involved in that. So the example couldn't be more simple, but it's on purpose. So now we can just imagine how much of a game changer it is. So in addition, we've added a user-directed way to reorient animations for a specific reference frame in animation. This is a super powerful feature, and it allows us to take animation that was authored in world space with large root offsets and reorient it within our cinematic without having to round trip to DCC. So here's an example when an environment change has come in that moved the log and Kelpie's animation no longer fits. You can see that she is clipping. Unfortunately, this animation has a root in world space very far away, which makes the rotating the animation very hard, since the offset is applied relative to the world space root. So you can see that we're rotating the animation now, and it looks like a slide because the pivot, the root, is extremely far away in front of Kelpie. So when using an offset mode on the root motion, a new option has been added to set the pivot of the animation trajectory around the current frame. So when you right-click on the animation, go to root transform and pick recenter, you can see now that we can rotate the entire animation around the current frame. And this is really like a game changer. Yeah, this is a game changer. So yeah, previously animation in sequencer was tightly coupled to UE's montage and an anim sequence infrastructure, whereas UEF allows us to take animation from anywhere and apply it anywhere. To allow for working with existing pipelines, the anim mixer track currently supports sending animation to UEF injection side and anim BP slot node, or take over the anim instance. And this is what sequencer calls the target. So animation sources within animation mixer also contain a priority value, where higher priorities override animation of lower priorities. Priority levels are blended together in a layered or override blending algorithm that animators are definitely familiar with. And this allows cinematic pipelines to mix animations together in layers and apply the result as a blend on the top of incoming pose. So for UEF, the target contains an injection site name, which is very familiar to anim blueprint slot nodes. Here you can see the UEF module first runs gameplay locomotion, which can be overridden by sequencer's injection sites. First the body animation and then the facial animation. When animated in sequencer, each animation section specifies the injection site it wants to target along with its priority. So it's exactly set on the animation event, and each injection site gets its own mixer that blends all the animation bands based on their priority and passes the result to the injection site. And then injection sites receive the pose from the upstream animation graph as its input, which allows it to be in total control of how cinematic animation is applied on the graph. This allows for animation mixing to happen directly in sequencer. All right, back to you, Andrew.
Thanks, Raf. So that's a little look at how we actually get into the cinematic. Let's think about how we get out of the cinematic. All those tools that Raf just demonstrated, we didn't use any transform tracks on any of the shots where we need to blend into and out of gameplay. This creates contention between whether the transform track wants to set the transform of the object or root motion, or whether the character movement component or mover is moving the character as well. So these tools allow us to feed transforms or the root motion naturally through the existing gameplay systems in a way that allows us to move seamlessly into and out of gameplay. So it turns out that actually blending back to gameplay is a much simpler problem, because we're going from a known keyframe state, which is deterministic, to back into gameplay, rather than the reverse, which is much harder to stitch together. In this case, first we re-enable player input so that the locomotion graph can begin to evaluate again based on where the player wants to be, and allows the locomotion graph to start generating trajectories and poses. At this point, though, sequencer still has priority over the pose, so it's still fully weighted, and everything that's happening in the locomotion graph is being overridden. And thanks to the new UEF architecture, we can read this pose, including the desired locomotion root motion delta, and interpolate that with sequencer's desired position. All the while, pose history is being correctly read and updated, such that pose searching for the locomotion pose in motion matching is giving us the best results throughout the transition, even though sequencer is partially in control. Of course, we also need to interpolate the camera back to gameplay, which is trivial with an easing curve on the camera cut track. And a note about camera transitions, we found that it's a good idea to stagger the timing and duration of camera animation and animation blends in order to help disguise the blends that are actually happening. So here's a blend back into gameplay from the demo where we see Kelpie running out of the forest. And at first it's being animated by Sequencer, and then we blend back into locomotion that's being controlled by the player. It's really as simple as that.
And yeah, and bear in mind that there are no transform tracks here, which is how we're able to seamlessly blend without different tracks fighting for the transform of the player. Yeah, all right. So let's move on to the topic of timeline scaling right now in localization. A big part of our design philosophy is to bring creative vision to the players around the world in a way that feels tailored to their language. And this goal requires us to think about the localization from the outset. And with this tech demo, we were able to work with our friends from Epic to develop robust timeline scaling tools. We want to deliver The Witcher 4 to our fans around the world. So let me show you now a really quick example of just one line being played in 3 different versions. So the first version would be the English performance capture with English voiceover.
Now. Kavir's smuggling trade is of no concern to me.
The other version is dubbed, so it's the English perf cap with covers just Polish voiceover.
Spokojnie. Kowirski przemyt zupełnie mnie nie interesuje.
And the third one is Polish voiceover with Polish lip sync overriding the perf cap.
Spokojnie. Kowirski przemyt zupełnie mnie nie interesuje.
So while Polish is not easy to understand, but you can clearly see how it settles visually and how close it is to the original, which makes it much more personal, in this case for Polish players. So if you hear any of your native languages aligned with lip sync, it just hits differently. So thinking about the game being immersive and engaging is one thing, but then we're here figuring it out how to deliver it technically. So just before we get into the technicals, let me give you a glimpse of how we're tackling the whole topic from the localization and cinematic design perspective. So when working with localized audio, you want to develop your project using a single consistent reference language to streamline your localization pipeline and to reduce the opportunity of errors. This language is the language that allows you to time everything perfectly and create the base for the algorithm. And it's the only language you work on when implementing cinematics. Then we need to closely work with the localization team to prepare all the voiceover lines to correspond to lines for recordings. We mark all the lines in game with specific time restriction tags, which correspond to the duration differences allowed on the actual recordings. And this is one of the most important things to do, a conscious pass on by designers, because this will later have an effect on how scenes are scaled. We have few types of those restrictions. For example, we have like 0% difference in length between languages, and this with exactly hits on emotional points and specific gestures. We have another one that's also 0% but doesn't have to hit. We have like 5% difference, 10% difference, but it's subjective to your project, right? And then we go into voiceover recordings. So as you might imagine, it's very hard to have all the scenes with in such scope of a game in performance capture because it's very, very expensive. Most of the scenes are covered with voiceovers later in recordings, and that is the reason those voiceover recordings are crucial for the scene experience. Cinematic designers are working very closely with localization team to deliver the most engaging lines. And we usually focus on providing actors with scene reference videos that are as close to the final shape as possible. But it's very tricky here because very often, you might imagine that recordings for all languages take very long time, so they need to start early in production, meaning that the scenes are also in a very early stage of implementation, and they have to be pushed enough to sell pacing and emotions to voiceover actors. So then we reached the point of implementing where voiceovers start to arrive from sound designers. We check how it works with animations in sequencer, sometimes adjust timings of those animation voiceover lines. But as stated at the first point, we only use the reference language. This is why we need scaling algorithm, because it's just impossible to implement every scene for every language in a separate file version. I mean, it's possible, but I don't know if you want to spend like 10 years doing that. So, you know, we just use it for like special cases. And although it might sound as a huge hassle, the whole pipeline, ability to scale timelines is a lifesaver to maintain large-scale production. So handing it over to you, Andrew, to talk about the tech.
Thanks, Raf.
Yeah.
So yeah, let's take a look at how we set this up. First off, as Raf said, it's really important to develop your content using a single consistent reference language, which will streamline your localization pipeline and reduce the opportunity for errors to be introduced. In Unreal, this is the language that you use for your default assets, the language that they're recorded in, and it will form the reference duration that Sequencer uses to retime elements on the sequence when the audio length changes. Once you have your reference audio in the engine, we create localized versions of those assets using the asset localization submenu, as you can see here. These localized versions are automatically swapped out depending on the current language of your game at runtime using Unreal's built-in package localization. And Sequencer then compares these versions with your reference language and scales the timeline accordingly. Once you've dropped the reference audio clips onto a level sequence timeline, you can enable this new option that we added called the scaling driver option. And this registers the clip with the scaling driver and enables scaling for that particular region of time based on its bounds. If you have localized facial performance capture or even full body animation that you want to localize with the audio as well, you can set the skeletal animation clips to linear playback when scaled, and this will allow them to change their time and scale their time to match the length of the audio, but it will still play back linearly at runtime according to wall clock time, which means that it will stay perfectly in sync with your animation, with your audio. And finally, we added a preview language drop down here. There's a lot of languages here. Maybe your project has that many, but if you switch the language out here, it will preview the results directly in Sequencer. It will switch out the audio, it will scale the timeline. And this whole feature is built on our time warp machinery that we added in 5.5. So you'll see the play rate naturally changing scale as it enters different audio clips. And here's what it looks like. As you can see, we toggle between two different languages here. They have localized audio on the top there. When we change the preview, the audio clip is stretching and squashing the timing of everything on the sequence within its range. As you can see, it's like super intuitive. We retime the keyframe positions, we retime events, we retime section start and end points. And the goal here really is for it to just behave as you would expect it to. So we were super happy to work with our partners at CD Projekt Red to establish these design goals that are critical really to the success of the feature in a large production pipeline. So these are all available in 5.6, and the new timeline scaling tools, they leverage time warp machinery, as I said, built into Sequencer to provide a robust retiming algorithm that's driven by the specific sections. And while we've implemented this for audio, the interface that it's implemented on, you can add to anything. And actually, you can add from anywhere. It doesn't even have to be a section within Sequencer. One of the things we want to add in the future is the ability to hand place anchors within the timeline, which allow you to stretch and scale things from specific points. That's not there yet, but we're hoping to add it soon. And these are the guarantees that we give in the algorithm itself to give you confidence that you're not going to see things being reordered and introducing bugs depending on various different conditions at runtime. So firstly, we guarantee that elements existing on the same frame before scaling will exist on the same frame after they've been scaled. So although it might not be the exact absolute frame number, they will still be aligned. Secondly, we guarantee that gaps between scaling drivers won't be scaled. And finally, elements that would exist within the range of a scaling driver will be at the same percentage along that scaling driver after they've scaled, with a caveat, and this is the complexity of the algorithm, that if you have overlapping scaling drivers where you have lots of overlapping audio clips, then although we do the right thing intuitively, you will see things shift slightly within the percentage difference. So Raf, over to you. Let's take a look at how it plays out with some examples.
All right, so now you will see 3 language versions played at the same time from the exact same frame, which is going to be English, it's going to be Polish, and it's going to be German. And please focus on how those versions spread from each other and how they come back together in some parts. And the audible video will be in the purple outline. So yeah, let's go.
A typical day's toil.
Who in? Ah, with Ciri. What news do my wagons? No eternity is taking that damn salt to arrive.
I found them. And, well, suffice to say,
Cóż, raczej do ciebie nie dojedzie. Swoją drogą soli to akurat tam nie było. Chociaż dla ciebie to pewnie żadna niespodzianka. Spokojnie.
Nur die Ruhe. Kovirs Schmuggelware kümmert mich nicht im geringsten.
Psst, psst.
Doch der Manticore, der deine Wagen zerstört und deine Männer verschlungen hat, hingegen schon.
Manticore? Nein. Nein, diese geflügelten Biester gibt's am Arsch der Welt, in Creme, nicht hier.
So yeah, like this was. So this was the algorithm in action, and you can clearly see how it works when you kind of align those versions all together at once. So yeah, that was it. Thank you very much, guys.
All right, how's it going? My name is Matt, and I'm excited to be here alongside Yushan today to show you how we brought Kelpie to life in the Witcher 4 Unreal Engine demo using Chaos Flesh and ML Deformer. So we're going to start with a quick overview of the asset setup to help give context. Then Yushan will dive into Chaos Flesh for simulating muscle and flesh dynamics. Next, we'll explore how we leveraged ML Deformer to adopt these simulations for real-time performance. And then finally, we'll share some of the key challenges we encountered along the way, and also some of the steps that we're taking to refine and improve our workflows. So here we meet Kelpie, and she's one of the most important characters in the game. Bringing her to life involved a combination of many systems, from animation powered by UEF to dynamics driven by control rig. Today, however, we're focusing on just one piece of that puzzle, and that's the deformation systems that we use to drive her soft tissue and skin. So the goal was pretty straightforward. We wanted to create the most believable horse, real-time horse, anybody had seen. And to help us achieve this, we wanted full muscle and flesh simulation for Kelpie, something that would bring a new level of realism to the character. And of course, we needed it to perform at a level suitable for a AAA games title, and that meant hitting 60 frames per second on PlayStation 5. And as I'm sure you guys have seen already, it's not just a simple tech demo. There's a ton of stuff happening on screen, from complex environments, lighting, and multiple characters, all running together in real time. So let's talk asset setup. So Kelpie is made up of two main mesh groups. So there's the render meshes, which you can see on the left. This includes Kelpie herself, plus the accessories and grooms. And then there are the musculoskeletal meshes, which you can see on the right. And these cover the skeleton, the muscles, and the fat layers. So the render meshes are driven at runtime using a mix of linear, skinning, ML Deformer, and control rig physics. The musculoskeletal meshes are used during simulation, and we use these to generate tech meshes, drive constraints and collisions. Like, we don't actually use these in runtime. So Kelpie has 4 LOD levels. LOD 0 is reserved for cinematics, while LOD 1 was active during regular gameplay. So the first 2 LODs run with ML Deformer, and the lower 2 just fall back to linear skinning. So LOD 0, which we can see at the top, this has around 30,000 verts, and about 2/3 of these have been driven by Chaos Flesh through ML Deformer. And at this LOD level, we increased the mesh resolution in 2 key areas, and you can see these highlighted in green. And this was to help better capture the muscle definition of movement in these regions. And so the mesh topology went through quite a few iterations, particularly as we fine-tuned ML Deformer performance. But since the render mesh is decoupled from the simulation, like, it's actually it's pretty quick to regenerate the geometry cache when we updated the topology. We didn't really need to run all the simulations again. LOD 1 comes in at just over half the resolution, under half the resolution of LOD 0. You can see that on the bottom. But due to how the topology is distributed, only about 1/3 of its verts are affected by ML Deformer. So while our main focus was simulating Kelpie's muscle and flesh, integrating the saddle straps was a real challenge. So we needed them to move with the underlying muscles and to not have any intersections. So using USD, we exported the Chaos Flesh geometry cache into Houdini, and we set up a simple FEM simulation on the straps. We simulated using the same training ROM structure as the Kelpie. We brought the results back into Unreal Engine and trained an ML Deformer on the result. CDPR built an anatomically accurate musculoskeletal model, and they fitted that to Kelpie's render mesh. So simulating every muscle isn't always practical or even helpful. So we did simplify and combine certain muscle groups to improve simulation speed and stability, but while also keeping the results physically plausible. And this anatomical setup extends all the way through to the animation joint layout. So this alignment is really important. So making sure the joints match the actual anatomical bones ensures proper biomechanical motion during simulation and animation, and it helps keep us in the realm of realistic deformation. And so while we continue to make small tweaks to muscle volumes and meshes throughout the process, the anim joints are tightly linked to both simulation setup and the animation pipeline. And so it was really important to lock these down as soon as possible. So in addition to simulating muscles, we also simulate the fat layer, which you can see here. And this is the connective tissue that sits between the muscles and the skin. So this is a closed watertight mesh, so it has thickness. The inner surface is effectively shrink wrapped to the muscles underneath, and the outer surface is pretty much aligned with Kelpie's skin. So the final piece is the skeleton and the collision meshes that help support the muscle geometry. So we didn't use a skeleton for collision. Instead, it drives the origin and insertion constraints for the muscles, effectively anchoring them to the skeletal structure. So where extra collision was needed to help keep the simulation on model, we added extra helper meshes, and you can see these here in green. Next, Yushan's going to take us how we brought these meshes together in the full simulation setup.
Thank you, Matt. With the amazing musculoskeletal assets that we set up for Kelpie, we use Chaos Flesh system to simulate Kelpie's muscle and fat on top of its animated skeleton. This allows us to go beyond traditional skinning approaches and deliver physically realistic body deformations, which is especially in game scenes like a galloping horse. Let's start with a high-level look at the layers of the simulation. First, we start with the standard animated skeleton from the previous asset setup section. From there, we add a volumetric simulation layer for muscles and fat driven by the animated skeleton. These soft bodies are simulated as tetrahedral meshes, allowing for realistic deformation that responds to elasticity, contact, and muscle contraction. We excluded the head, tail, and hooves because they do not produce significant muscle-related deformations and can take up a huge amount of simulation time. Once the muscles and fat are simulated and cached, their deformation is transferred to the render mesh, which is the final visible surface in the game. Finally, with the geometry cache containing the render mesh positions, we can train an ML deformer that can emulate expensive offline simulation at the real-time cost. Before diving into our simulation setup, I just want to emphasize that the horse simulation is quasi-static, meaning that there is no dynamic components, and for each pose, the simulation will always produce the same result. This allows us to have deterministic training data for our pose-driven ML deformer. We use data flow graph system to procedurally generate Chaos Flesh assets that are used during the simulation. The full setup on Kelpie can be broken down into several sections. First, import the assets and generate tetrahedral meshes for volumetric simulation. Next, paint muscle origins and insertions and use them to compute muscle fiber field and set up muscle activation. After that, create kinematic and spring muscle constraints to drive the simulation. And lastly, embed the render mesh for transferring deformation from the tetrahedral mesh to the render mesh. It's a streamlined data flow setup designed to be artist-friendly, and we have added various tools for quick simulation tests and debugging. We first import the muscle surface mesh and generate a tetrahedral mesh. The tetrahedral mesh is essential for a volumetric simulation, allowing us to compute material stress and constraint forces on tetrahedral vertices. We use FastTetWeld to robustly convert surface geometry into simulation-ready tetrahedral meshes. Inside our data flow node, we can also control mesh resolution parameters, such as ideal edge length and surface preservation to find the ideal balance between runtime and mesh quality. Next, let's define muscle origins and insertions. There are muscle attachment points connected to bones and drive the muscles as kinematic constraints. We use a painting tool in the data flow system to paint muscle origins and insertions on the muscle surface mesh, which are then transferred to matching muscle in the tetrahedral mesh. This approach allows us to freely adjust the resolution of the tet mesh for quick tests without worrying about losing the progress on the surface mesh. Now, for each muscle, we can compute a gradient field that mimics how the muscle fiber flows from muscle origin to insertion. It is based on solving a Laplacian equation. Think about like heat propagation through a muscle from one end to the other. And the muscle fiber direction will be the gradient of the scalar heat field. Now with muscle fiber field, we can define muscle contraction. On the per tetrahedron level, each muscle contracts along the fiber direction and expands in the orthogonal directions. This gives us a natural-looking contraction and bulging behavior. Now we define muscle contraction, we can control muscle contraction effects with customized parameters. For example, we can modify muscle volume when it's contracting, as well as rest muscle volume to make the character either buff or skinny. Muscle contraction length is also parameterized along the length activation curve that defines the muscle activation model. Using global parameters allows us to do quick setup and test, while per muscle customization allows fine-grained control over simulation behavior. We also support computing muscle length from a representative training animation for automatic fitting on the contraction length parameter. So far, we know how the muscles contract, but the question is, when do we make them contract? For each pose, we can first define muscle length to be the distance between the kinematic muscle origin and insertion. We can use the ratio of the muscle length to its rest length to compute muscle activation. The idea is that if a muscle gets shorter than its rest length, it's probably actively contracting. By default, muscle activation is linear to muscle length, but the curve can be modified either globally or on a per muscle level. While computing muscle activations can be automatic based on changes in length, we can also drive them artistically. We created 30 animation curves on Kelpie and mapped them to corresponding muscles in data flow graph. And we can craft precise muscle activation using curve values in time. One example is that when Kelpie's hoof land on the ground, its glues can be independently activated by the curves. Here's a muscle simulation that uses curve-driven muscle activation on 30 muscles. Each muscle goes from being inactive to fully active. Now to propagate pose changes on the animated skeleton, we apply kinematic constraints between muscles and bones based on distance. We also create sliding spring constraints between muscles to hold the muscles together like a fascia does. We support different types of springs, either sliding, sticky, fixed length, or zero rest length springs, and they can be tailored per region to handle tricky anatomical structures. We also simulate collision volumes and fat alongside muscles. Collision volumes provide internal support between muscles and bones. We created sliding spring constraints between muscles, collision volumes, and fat, allowing for deformation propagation all the way to the surface of the fat. Finally, the render mesh is embedded in the fat layer, therefore inherits all the subtle deformations on the fat layer. Now that we have prepared all the tetrahedral meshes, we can run a quasi-static simulation and generate training data for ML deformer. The reason for a quasi-static simulation, again, is that ML should produce the same output for a given input pose. Therefore, the training data should be deterministic and have no dynamic component. In SIGGRAPH 2024, we published position-based nonlinear Gauss-Seidel solver, which is specifically designed for this task. Because traditional PBD solvers do not support quasi-static simulation, and they suffer from fighting constraints. Our solver is robust under low computation budget and converges to the true solution if given sufficient budget. The tetrahedral mesh simulation results are finally saved in a chaos cache for playbacks. And from that, we generate a geometry cache of the render mesh by interpolating from the tetrahedral mesh simulation. The geometry is later used as training data for ML deformer. Our full muscle and fat simulation includes over 290,000 vertices and 860,000 tetrahedra. It runs at around 25 seconds per frame, 36-hour total for 5,000 frames on a high-end 128-thread CPU. This allows us to iterate on ML deformer results in a matter of a few days. Let's take a look at the muscle simulation on a Gallop animation. Notice how the leg muscles contract, and the leg moves back and forth. Again, muscle activation here is controlled by muscle length, which means whenever muscle length gets shorter, following the animation, the muscle starts to contract. Now that we've looked at the full simulation setup for the horse, I just want to show you how fast and streamlined Chaos Flash system is by setting up a bicep simulation from scratch in under 5 minutes. We'll start with the empty data flow graph. There we're bringing in the skeleton. You can see it in a second. There it is. Also bringing in a bicep skeletal mesh. Here you see it. Now at this point, let's create a volumetric mesh for the bicep. This process usually takes about 20 seconds to generate a high-resolution TET mesh. There you have it. Let's set mass and stiffness on the tetrahedral mesh, and then attach a terminal. Free fall. There you go. Just make sure everything runs OK. Now let's bring in the skeleton and use that to drive the bicep eventually. Set animation on it, and create some kinematic constraints between the bicep and the bones. Tweak some simulation parameters. Let's run it. Now you can see we can drive the bicep with the bones. It doesn't look quite real like a real muscle, right? Let's make it more real. Let's start painting muscle origins, insertions, so that we can contract the muscle. Now there's the insertion. This is a data flow painting tool, by the way. And now we'll paint it on the skeletal mesh. We can transfer that to the tetrahedral mesh, the volumetric one. You can see the transfer results. They're in white. Let's extract the vertices of origins and insertions. Now compute muscle fiber field using those vertices. You see it's color-coded from blue to red. And we can visualize the fiber, muscle fiber there. Also compute muscle activation data. We're going to need those for muscle contraction. Set up muscle parameters. And again, attach the terminal node. Make sure enable muscle activation in the stem. Now you should have a basic muscle contraction. We're going to make that more obvious by increasing the contraction volume parameter. Let's increase that from 1 to 2. Now you should see more obvious muscle contraction. We can also change that to 3 to make it kind of ridiculous. I also revert that, and then instead, let's make the character really muscular. You can do that too. Let's change the rest volume scale from 1 to 3. Boom, your muscles start to inflate. And that's all I want to show you, from an empty graph to a fully driven and contracting bicep muscle in just under 5 minutes. Now I'm going to hand it back to Matt for ML Deformer.
All right, so Chaos Flash, as you've just seen, delivers really awesome results, but it does come at a cost. So as Yushan mentioned, each frame takes around 30 seconds to simulate, which is pretty good. But for Kelpie, we need to achieve similar results in 0.2 milliseconds. And so this is where ML Deformer comes in. So it compresses our high-fidelity simulation into a lightweight neural network and a set of morph targets, enabling fast evaluation with minimal loss of quality. So let's take a look at a bird's eye view of Kelpie's deformation system. So this is structured in layers, and each layer adds a specific level of detail and control. So at the foundation, we have the standard scarlet mesh, just uses linear skinning. on top of this, we apply the first of our 2 ML deformers. And this deformer is driven by the character's pose. With our second ML deformer, we add animator-driven activations, muscle activations. And then finally, we add overlapping motion with dynamic jiggle driven by control rig joints. So the core ML deformer is a local neural morph model, and it's trained on 5,000 frames of chaos flesh simulation. So there are 23 bones and 5 bone groups as inputs to the network, and these inputs are joint rotations. And so the deformation has been driven by Kelpie's pose. But as we know, that's not how things work in the real world. So muscles don't only react to pose or movement, they also respond to load. So think of holding a heavy object. So your pose might not change, but your muscles definitely activate. And so we want the same behavior for Kelpie, right? So when a who's hit the floor, we want to see her leg muscles visibly contract from the impact and the loading. So this is where the activation layer comes in. This is an additional ML deformer that applies additive deltas on top of the core ML deformer. So this means deformation is no longer limited to just pose. It can also be driven by animator-authored curves, and this gives us pose-independent control over muscle behavior. So here, I've just highlighted some muscles that are available in the right shoulder region of the body. And now let's take a look at a time lapse of the keyframing workflow we use to animate them in the gallop cycle. Right, so because this layer is artist-driven, animators now have a high degree of creative control. They can art direct exactly when and how muscles activate, and this allows for more expressive and more intentional results. So here you can see how each layer combines to give us the final result. On the far left is just linear skinning. In the middle is our core pose-driven layer, and it's this ML deformer that does really most of the heavy lifting. But it's the muscle activation layer that we see on the right that really adds that extra layer of detail and realism, and it really helps bring Kelpie to life. So let's refresh ourselves on the basic workflow for ML deformer. So the first thing we need to do is we need to author the range of motion, or ROM animation. So this sequence is designed to push the rig through its full range of movement. And this ensures the training process sees every possible pose that the character might adopt. We then run chaos flesh simulation on this ROM, and this gives us the geometry cache. This is the target deformation that we want the deformer to learn. And then with training data in hand, we configure the network parameters, we train the model, and then we validate the results to ensure accuracy and generalization. So this shows the training ROM for the core pose-driven ML deformer. On the left is our skeleton mesh. It's playing the animation, the training ROM. And on the right is the geometry cache that we've generated from chaos flesh. So this is the target deformation that we want the deformer to learn. So as I said, this is 5,000 frames of animation, and we generated the ROM by sampling Kelpie's gameplay and cinematic animations. We'll get into this a bit more later. So this is the training ROM for our activation layer. Because this layer is additive, we learn these muscle contractions in reference pose. And so you can see each muscle firing in the heat map visualization. So instead of bones, the inputs to this network are animation curves. And these are located on the root joint of the character. Each curve controls the contraction of a single muscle. We set this up for 30 muscles in total. Each activation in the training ROM is triggered over 10 frames. And that gives us 300 frames of training data. And really, the training ROMs are the most critical part of all of this. So a well-designed ROM ensures that the model is trained on meaningful and representative data, and they have a huge impact on both our workflow and also the final result. But generating these can be a real challenge. So over the last couple of years, we've put a lot of effort into making improvements here. And using my little biped dude as an example, Let's take a look at how this has evolved. So our first ML Deformer demo used a training ROM that was made out of 7,000 frames of per joint random rotations. It was super fast to generate this type of ROM, but it came with a ton of problems. So a lot of the poses are not physically plausible, and you get a ton of self-intersections, right? So this made the dataset really inefficient, and it causes lots of problems for simulation-based workflows. And at the time, we managed to work around it, and we did get to a good result, but it was really hard, and it required a ton of manual cleanup. So it was obvious we needed to find a better solution. And that was to use in-game animations, or full-body ROMs. And to do this, we added an animation sampler to our Maya plugin. So this sampler, basically, you feed it a folder of animations, and it picks the most useful poses to build a compact, high-coverage ROM. Unlike the random pose generator, however, this method generates a ROM full of correlated movements, and you can see some examples of this here. So people would tend to shrug both shoulders together or raise their arms together, and this causes real problems for the models. So for these sorts of poses during training, there's not enough independent left-right motion to allow the network to untangle the two sides. And so this can lead to issues in the final deformer where when you animate a right arm, we see deformations on the left. And obviously we don't want that. So to combat this, we added bone masking to the local neuromorph model. And during training, these masks basically tell the model, hey, for this network input, only consider deltas within the masked region. This prevents the model from associating deformations with the wrong inputs, and it allows training on this kind of data. So on the left is our full 10-minute or so body ROM, and the orange guy next to him, this is our sampled animation. So as you can see, all the poses are physically plausible. We don't get any self-intersections. Now every pose counts. Our ROM size dropped by 40%. And this is also great for simulation-based workflows. Didn't require the cleanup that we'd needed previously. The problem, of course, is that only the local neuromorph model supports bone masks. Our other models still have to be trained on random data. So fast forward to 24. As part of the demo, we want to show an ML deformer trained on cloth simulation. Now, we knew at the time that the local neuromorph model wasn't really suitable for this use case. But as we knew, our other models couldn't be trained on anim-sampled ROMs. And we didn't want to go back to random order-based ROMs. That was an option. We'd already experienced the limitations there. So we introduced a new solution, and that was region-based temporal resampling. So this is an additional processing step, and it takes our anim-sampled ROM, and it reorders the keyframes by regions. And you can see the region groupings that we used here. So again, full 10-minute pose, full 10-minute body ROM on the left. On the orange guys are anim sampled, and then the new yellow guy, this is our region resampled. So you should be able to see that this decorrelates our motion while still preserving physical plausibility. And so the result of this is that all of our models can now be trained on data derived from actual animation. Whether that's keyframed or motion captured, game database, or a full body ROM. And this really unlocks significant workflow and quality improvements across all of our models. So now it's 2025. Now we're training ML Deformer for Kelpie using Chaos Flash simulation. So we know already now that we can generate a good training ROM by sampling from Kelpie's animation database and remixing the poses. The remaining issue is that the pose difference from one frame to the next is too great for continuous simulation. In the past, we've added 9 frames of warm-up for each training pose. So for a 5,000 frame training ROM, we're simulating 50,000 frames and then throwing away 90% of them. And with Chaos Flash still under heavy development and at sim times at 30 seconds per frame, that's 17 days of simulation time, and that's far too long for any kind of meaningful iteration. So again, we rethought the process. Instead of sampling 5,000 frames, we sampled just 500. We again used our temporal resampling to decorrelate motion, and then we scaled the result of that by 10. And this gave us the 5,000 frames of animation suitable for continuous simulation. And we simulated and trained the deformer on just those 5,000 frames. And so the result was really a 90% reduction in simulation time, and it enabled rapid iteration on both simulation, rigs, and tooling without compromising on the final deformer quality. So now we're in a position where sampling your animation database is a really great way of generating training ROMs for ML deformers. But it can be a challenge, particularly if you're working in parallel with animation teams, and those are constantly changing. And depending on where you are in the project, you might not have any animations, and that makes it really hard to get started. Well, for bipeds at least, we've got you covered. So the full 10-minute body ROM, the one I showed here, the same one that we use internally for our own production-ready deformers, is available through the ML Deformer Marketplace sample. The QR code for that is on the top right. And out of the box, this gives you a high-quality starting point for building a biped ROM that's going to work across all model types and training workflows. And to make things even easier, the animation, sampling, and remixing tools that we originally released as a My plugin, the QR code is the second one there. These are now also available in Unreal, and you can access these tools via the Tools menu of the ML Deformer Editor window. This allows you to sample your animation databases and generate training ROMs without leaving the editor. So I spent a lot of time discussing the ROM, but let's shift focus to some of the features and best practices that helped us deliver. So one of the most important principles when setting up your ML Deformer is to try and reduce complexity. So we want to make sure the network is only learning what's important. This allows for smaller ROMs, faster iteration times, and it's going to lead to a better result. So you want to start by limiting your network inputs only to what is essential. Like when you're setting up, there's a tempting option that asks if you want to auto-populate the inputs with all animated joints. You almost never want to do this. Instead, only include joints that directly influence the region that you're trying to learn. So, for example, if you don't want to learn deformation around the fingers, you don't want to be including those joints. Region masking lets us exclude areas from being influenced from the model. And there are two types of masking available. So there's vertex attribute masks, which is shown here in the red at the top left. So we set these up before training. These are painted directly in the Scalable mesh editor, and it basically allows us to exclude vertices from the training process altogether. The second are vertex color masks. Some examples are shown here in blue. These give us finer control over the transition between areas influenced by ML Deformer and those just using standard linear skinning. So, for example, on the bottom right here, you can see we've maxed out ML Deformer deltas at the base of Kelpie's main. And since the main only uses linear skinning, this ensures a clean connection between the two skeletal meshes. We now also support multiple pairs of training data, and this really helps speed up model iteration, particularly when animation databases are still being developed in parallel. So when new or updated animations emerge that aren't covered by your existing training ROM, we don't have to regenerate the entire training set or re-simulate thousands of frames. Instead, we can create smaller, targeted training sets that focus solely on the new or revised animations. And then we can add these alongside our existing data for training. And this enables faster and more efficient updates. And generally, you want to focus on ROM structure and reconstruction quality first. And these two things really go hand in hand. Before you commit to heavy simulations, it's a really great idea to test your ROM with something that's fast to generate. You can crank out 5,000 frames of test data and be ready to train in just a few minutes using simple deformers like Myers Delta Mush. And this is a really great way of validating your ROM, and it allows you to fail early and cheaply. It also allows you to test your ROM independently of other factors, right? And this can be helpful when we need to debug things further down the line. And once you start training, the main lever you can pull to increase quality is to increase the number of morph targets. So for the local neural morph model, we define morph targets per input. So essentially it scales with the network size. So even a small bump from 8 to 10 can make quite a big difference. In global mode, the default is just 128 morph targets. For something of Kelpie's complexity, I would say that's actually pretty low. And it's reasonable to double, or perhaps even triple that right off the bat to get better fidelity. Increasing learning iterations can be very helpful. So generally, more complex systems require more training data and therefore more training iterations. So by way of example, Kelpie's final base layer was trained on 25,000 iterations. The activation layer is much more simple. That only required 3,500. And finally, if you're still having issues, maybe you just don't have enough samples in your ROM. And I find a good starting point for a biped or quadruped, something of Kelpie's level of complexity, is around 5,000 frames. You might need more or less depending on what you're doing. If your deformer is underperforming in certain poses, then actually maybe your ROM's just lacking examples in just that one area. And with the multiple training pairs, you can now easily add additional training sets that gives you coverage of that region and retrain. So once your deformation is a good place, now's a good time to start focusing on performance. While you're doing this, it's really helpful to check the GPU memory usage stat, and that's at the bottom left of the ML Deformer editor. So for PS5, my rule of thumb was really that for every 10 megabytes of GPU memory, we're looking at around 0.15 milliseconds of GPU evaluation time. And Kelpie's LOD0 base and activation layer came in at 9.8 megabytes of GPU memory, so it's pretty quick. Reducing the number of morph targets is usually a good first move. You can trim those down until you start noticing an impact. And then from there, increasing regularization. This helps make morph targets more sparse and efficient. It can sometimes lead to artifacts. Generally, I'll tend to set this straight away from 0 to 1, and then step it back down if I notice any problems. Boosting compression is a really quick win for performance. You don't need to retrain the model after changing these values. And finally, you can squeeze out some extra performance by optimizing your inputs and masks. Obviously, at this point, if you still need to find additional performance, you might need to look at reducing mesh topology and implementing LODs. It's the same process that we went through for Kelpie at this stage. And as I said, it's actually pretty easy to regenerate Chaos Flash geometry cache on new topology. We don't need to run the full simulations again. When you are iterating, it's super helpful to be able to compare your latest changes against the previous version. And you can do this really easily. There is a compare actors array in the testing mode, highlighted here. So you just need to reference in another deformer, and you get a side-by-side comparison to see exactly what's improved or not. And I mentioned LODs on a previous slide. Generating ML deformer for lower LOD meshes is super easy. All you need to do is change that number there to anything greater than 1, and this will automatically generate a set of morph targets for the low LODs, and it will hook them into the network for you. So you don't need to manually generate or manage that data yourself. So obviously we had plenty of challenges along the way. Since Chaos Flash is still experimental, development has mainly focused around the core features and solver improvements. And that means, some of the more artist-friendly workflows, quality of life features that we want to push in haven't been a priority. And so while the system is incredibly powerful, it's not always easy to take advantage of that at the moment. We sometimes ran into issues where the fat could get pinched between muscle volumes. We struggled a bit, in this region of the rear leg, where the animation poses would swing the leg in too far, and this would cause interpenetration. USHAM wasn't able to improve the simulation stability to help mitigate this, but it does highlight a bit of a common challenge with simulation rigs in general. So, even though we're using a high-quality gameplay animation set to generate a training ROM, those animations aren't always designed with simulation in mind, so you can occasionally run into these issues. One of the other challenges we touched on earlier was driving secondary meshes, like saddle straps based on the deformation of the underlying surface. Combining this with physics and avoiding intersections all at the same time proved pretty tricky. And to generate training data from the straps, I mentioned we used a Houdini-based workflow layered on top of the Chaos Flash simulation. This worked, but it wasn't the most efficient or streamlined approach. So looking ahead, one of our key goals is to simulate these kind of secondary elements directly in Unreal, either at runtime or as part of the ML Deformer training process. We really want these tools and workflows to be available to everybody, and for them to be fast and intuitive. And these sort of lingering dependencies to DCC, kind of run against that a little bit. We're also exploring several areas to push the system further. So cloth and flesh integration, we want to support two-way interactions, enabling skin simulation layered over deforming fat and muscle for even more realistic results. We would like advanced activation models, moving beyond simple muscle length-based activation to more sophisticated physically informed models. We want better artist control. We want to give artists more direct control over muscle behavior and deformation with more intuitive tools and parameters. And finally, we want quality of life improvement. So this includes better tool integration, automated workflows using data flow subgraphs, and also ongoing solver optimizations to improve performance. And finally, to wrap, I'm just going to leave you with this little breakdown video of how it all came together. Thank you very much. Happy to take any questions if anybody has any.